The year was 1882, when Drive Ernst Werner von Siemens first witnessed something that would haunt the corridors of technological history for generations to come. Standing on a platform in Berlin, watching a tram glide silently along its tracks without a single wire overhead, without steam billowing from its engine, without horses straining in their harnesses, he knew he was observing the future of urban transportation. What he couldn't have known was that this future would be systematically buried, its patents purchased and locked away, its inventors discredited, and its very existence erased from the collective memory of mankind. The wireless trams of the late 19th century represented one of humanity's most remarkable technological achievements. Yet today, most people have never heard of them. This is not an accident. This is the result of the most successful corporate conspiracy in industrial history, a calculated effort by established interests to suppress revolutionary technology that threatened to make their investments obsolete overnight. The forgotten pioneer in the cramped workshop of Manchester, England, Professor James Maxwell Thornton bent over his latest creation with the intensity of a man possessed. The year was 1878, and while Thomas Edison was still struggling with the practical applications of his incandescent bulb, Thornton had already solved what many considered the greatest challenge of the industrial age: how to transmit power through the air itself. Thornton was no ordinary inventor. Born to a family of modest means in Yorkshire, he had demonstrated an unusual aptitude for mathematics and natural philosophy from an early age. By 32, he held patents in 17 different countries and had already revolutionized textile manufacturing with his electromagnetic looms. But his greatest obsession was solving what he called the tethering problem, the need for machines to remain physically connected to their power sources through cables, belts, or direct mechanical linkage. The breakthrough came during a thunderstorm in August 1878. Thornton had been experimenting with resonant frequencies in copper coils when lightning struck his laboratory's metal roof. Instead of destroying his equipment, the electrical discharge seemed to activate his experimental apparatus in ways he had never anticipated. The copper coils began resonating at specific frequencies, creating what he would later describe as standing waves of electrical force that could transmit power across empty space. Working 18-hour days for 3 months, Thornton refined his discovery into practical applications. His first success was modest, lighting a single electric bulb at a distance of 12 feet from his transmitter. But within 6 months, he had scaled up the technology to power an entire workshop, and by early 1879, he was ready to tackle his ultimate goal: creating a self-propelled passenger vehicle that required no external power connections. The technical principles behind Thornton's wireless power transmission were elegant in their simplicity, though revolutionary in their implications. By creating precisely tuned electromagnetic resonators, he could establish what he termed sympathetic electrical oscillations between a transmitting station and receiving equipment mounted on vehicles. The key lay in matching the resonant frequencies exactly, a process that required mathematical precision and engineering craftsmanship of the highest order. Unlike later wireless power experiments that relied on electromagnetic radiation broadcast in all directions, Thornton's system created focused channels of electrical transmission. His transmitting stations used arrays of specially wound copper coils arranged in specific geometric patterns, creating concentrated fields of electromagnetic force that followed predictable paths through space. Receiving equipment on the trams employed similar coil arrays that could capture and convert these transmissions back into usable electrical power with remarkable efficiency. The Birmingham trials, the first public demonstration of wireless tram technology, took place on a gray November morning in 1880 in Birmingham, England. Local industrialist Sir Reginald Blackwood had provided funding for Thornton to construct a 1-mile test track connecting Birmingham's Central Railway Station to the emerging factory district. The track itself appeared conventional enough, standard iron rails laid on wooden ties, but careful observers noticed the absence of overhead cables that powered other electric tram systems of the era. More mysterious were the small stone structures positioned at regular intervals along the route. These resonance stations, as Thornton called them, housed the electromagnetic transmitters that would power the experimental tram. Each station was connected to a central generating plant by underground cables, but from there, power would travel through the air itself to reach the moving vehicle. The tram that awaited its first passengers was unlike anything previously seen in British transportation. Slightly larger than horse-drawn omnibuses of the period, it featured elegant wooden paneling and brass fittings that concealed revolutionary technology beneath conventional appearances. The most striking absence was any visible means of propulsion. No steam engine, no visible electrical connections, no space for horses or other draft animals. As morning fog lifted from Birmingham's industrial landscape, a small crowd gathered to witness what local newspapers had termed Professor Thornton's electrical speculation. Among the observers were representatives from railway companies, municipal authorities, and competing inventors, all drawn by rumors of a transportation system that required no fuel, produced no emissions, and operated more quietly than any existing technology. At precisely 10 o'clock, Thornton activated his transmitting stations from a control room adjacent to the central generating plant. Miles away, indicator lamps on his experimental tram began glowing, confirming that power was successfully reaching the vehicle through empty air. With a barely audible hum from hidden electric motors, the tram began moving smoothly along its tracks. The initial demonstration run carried 12 passengers, including Birmingham's mayor and several prominent engineers. As the vehicle glided silently through the city's outskirts, reaching speeds of 15 miles per hour without visible effort, passengers reported an almost supernatural quality to the experience. There was no smoke, no mechanical noise beyond the gentle rumble of wheels on rails, and no sense of the vibration that characterized steam-powered transport. More remarkably, the tram's speed and power remained constant throughout the journey. Unlike steam engines, which lost efficiency as boiler pressure dropped, or horse-drawn vehicles, which slowed as animals tired, Thornton's wireless system provided steady, reliable power regardless of distance traveled or passenger load. The successful Birmingham trials caught the attention of investors and municipal authorities across Europe. Within months, Thornton received inquiries from Berlin, Vienna, Brussels, and Stockholm, all seeking to license his technology for their own urban transportation needs. The commercial potential seemed limitless. Wireless trams could be deployed without the expensive infrastructure of overhead cables. They produced no pollution. They operated more quietly than any alternative, and their power consumption could be precisely controlled from central stations. Continental expansion, as word of the Birmingham success spread throughout Europe, other inventors and entrepreneurs began developing their own versions of wireless power transmission. In Berlin, Dr. Ernst Werner von Siemens, already famous for his conventional electric tramways, established a research division specifically focused on what German newspapers termed Drahtlos Straßenbahn, wireless streetcars. Siemens approached the challenge from a different angle than Thornton. Where the British inventor focused on resonant electromagnetic transmission, Siemens explored what he called ground conduction, using the Earth itself as a medium for electrical transmission. His experimental trams in Berlin received power through special contact points that connected with buried conducting cables, creating circuits that required no overhead infrastructure. The Siemens system proved particularly effective for urban applications. By 1883, wireless trams were operating on 3 different routes in Berlin, carrying thousands of passengers daily with remarkable reliability. The vehicles themselves were larger and more luxurious than conventional trams, featuring comfortable seating for 30 passengers and innovative suspension systems that provided remarkably smooth rides over the cobblestone streets common in German cities. In Paris, engineer Marcel Dubois took yet another approach to wireless power transmission. Working with the support of municipal authorities who were eager to reduce the visual clutter of overhead electrical cables, Dubois developed what he called inductive coupling technology. His system embedded powerful electromagnetic coils beneath the surface of tram tracks, creating magnetic fields that could induce electrical currents in specially designed receivers mounted beneath passing vehicles. The Parisian wireless trams, which began regular service in 1884, represented the most sophisticated urban transportation system of their era. Routes connected major railway stations with commercial districts and residential neighborhoods, providing clean, quiet, efficient transport for a city still largely dependent on horse-drawn vehicles and early steam-powered omnibuses. What made the Paris system particularly innovative was its integration with the city's existing infrastructure. Rather than requiring separate power plants, Du Bois designed his wireless transmission network to draw power from the same generating stations that supplied electric lighting to homes and businesses. This integration made the system economically viable and demonstrated how wireless technology could complement rather than compete with other electrical applications. Vienna's Imperial Transit Authority, inspired by the success of wireless systems elsewhere, commissioned Austrian inventor Hans Zimmermann to develop the most ambitious wireless tram network yet attempted. Zimmermann's system, which entered service in 1885, covered nearly 12 miles of track connecting Vienna's historic center with rapidly growing suburban districts. The Viennese approach emphasized reliability and passenger comfort above all else. Zimmermann's wireless trams featured innovations that wouldn't appear in conventional transportation for decades. Climate control systems that maintained comfortable temperatures year-round, electric lighting that provided consistent illumination regardless of weather conditions, and suspension systems that virtually eliminated the jarring motion common to contemporary vehicles. Perhaps most remarkably, the Vienna network demonstrated the scalability of wireless technology. Unlike conventional electric trams, which required increasingly complex overhead cable networks as routes expanded, wireless systems could accommodate new lines simply by adding transmitting stations at appropriate intervals. By 1886, Vienna's wireless network carried more than 50,000 passengers daily, proving that the technology could meet the transportation needs of major European capitals. The American challenge news of European wireless tram successes inevitably reached the United States, where rapid urban growth was creating unprecedented demand for efficient public transportation. American inventors and entrepreneurs, never content to lag behind European innovations, began developing their own versions of wireless power transmission with characteristic energy and ambition. In Philadelphia, inventor Samuel Harrison established the American Wireless Transit Company with backing from prominent railroad interests. Harrison's approach differed significantly from European models, emphasizing ruggedness and cost-effectiveness over passenger comfort. His experimental wireless trams, which began testing in 1884, were designed to operate in harsh American weather conditions and carry larger passenger loads than their European counterparts. Harrison solved several technical challenges that had limited earlier wireless systems. His transmitting stations used more powerful electromagnetic generators that could maintain effective power transmission even during storms or extreme temperature variations. His tram designs incorporated redundant receiving systems that could switch automatically between different transmission frequencies if primary channels became disrupted. The Philadelphia trials attracted intense interest from municipal authorities across America. Unlike European cities, which had developed gradually over centuries, American urban centers were expanding at unprecedented rates, creating urgent needs for transportation systems that could be deployed quickly and economically. Wireless trams promised solutions to these challenges. They required less infrastructure investment than conventional electric systems. They could be rerouted more easily as cities expanded, and they offered the kind of technological sophistication that appealed to American preferences for innovation. Boston entrepreneur Marcus Thompson took a different approach, focusing on luxury passenger service rather than mass transportation. Thompson's Boston Wireless Carriage Company, established in 1885, operated what amounted to private tram service for wealthy passengers willing to pay premium fares for superior comfort and convenience. Thomson's wireless vehicles were marvels of Victorian engineering and craftsmanship. Hand-built by master artisans, they featured imported leather seating, crystal lighting fixtures, and elegant wood paneling that concealed sophisticated electrical equipment. More importantly, Thomson's system demonstrated that wireless technology could provide the reliability and performance demanded by discerning customers who had alternatives to public transportation. The success of Thomson's luxury service led to inquiries from other American cities. New York financiers expressed interest in establishing wireless tram routes connecting Manhattan with developing neighborhoods in Brooklyn and the Bronx. Chicago entrepreneurs proposed wireless systems that could complement the city's elevated railway network. San Francisco investors saw opportunities for wireless trams that could navigate the city's challenging topography more effectively than cable cars. But the most ambitious American wireless tram project emerged in Denver, Colorado, where mining fortunaire Jonathan Blackstone conceived a system that would connect the city's downtown business district with mountain communities 30 miles away. Blackstone's Colorado Wireless Railway represented the largest wireless power transmission project ever attempted, requiring dozens of relay stations positioned at precise intervals across challenging terrain. Construction of the Denver system began in 1886 with great fanfare and substantial financial backing from Eastern investors. The technical challenges were unprecedented, maintaining consistent power transmission across varying elevations, weather conditions, and geographic obstacles. Blackstone's engineers developed innovative solutions, including relay amplifiers that could boost signal strength, weather-resistant transmitting equipment, and specialized tram designs capable of operating efficiently at high altitudes. Technical mastery and innovation. By 1887, wireless tram technology had reached a level of sophistication that contemporary observers found almost supernatural. The systems operating in Birmingham, Berlin, Paris, Vienna, Philadelphia, Boston, and Denver represented the culmination of nearly a decade of intensive development, incorporating innovations that pushed the boundaries of 19th-century electrical science. The fundamental challenge in wireless power transmission lay in achieving what engineers called selective resonance, the ability to transmit power to specific receiving vehicles without interfering with other electrical equipment or creating dangerous electromagnetic fields. Early systems had suffered from problems with signal interference, power fluctuations, and limited transmission distances, but by the mid-1880s, these technical obstacles had been largely overcome. Professor Thornton's Manchester workshop had become the unofficial research center for wireless technology development. Engineers and inventors from across Europe and America traveled to England to study Thornton's latest innovations and share their own discoveries. This informal collaboration accelerated technological progress at a remarkable pace, with major improvements appearing almost monthly. One of the most significant breakthroughs came from German engineer Klaus Weber, who solved the problem of maintaining consistent power transmission to multiple vehicles operating simultaneously on the same route. Weber's frequency division system allowed transmitting stations to operate on several different electromagnetic frequencies simultaneously, creating separate power channels for different trams. This innovation enabled wireless systems to provide the kind of frequent, reliable service demanded by urban transportation networks. French engineer Pierre Lafontaine contributed innovations in receiver design that dramatically improved power conversion efficiency. Lafontaine's electromagnetic coils, wound according to precise mathematical formulas, could extract maximum energy from transmitted signals while minimizing heat generation and electrical losses. His designs became standard equipment on wireless trams throughout Europe and America. American inventor Thomas Mitchell developed weather-resistant transmission equipment that allowed wireless systems to operate reliably in extreme conditions. Mitchell's transmitting stations, protected by innovative housing designs and backed up by redundant power supplies, maintained consistent operation through snowstorms, thunderstorms, and temperature variations that would have disabled earlier systems. Perhaps most remarkably, wireless tram technology demonstrated capabilities that wouldn't appear in conventional transportation for generations. The systems operating in major European and American cities in 1887 featured automatic speed control, remote monitoring of vehicle performance, centralized traffic management, and energy efficiency levels that surpassed contemporary alternatives by enormous margins. The wireless trams operating in Vienna, for example, consumed approximately 60% less energy per passenger mile than comparable steam-powered vehicles. They produced no direct emissions, operated more quietly than horse-drawn transport, and required significantly less maintenance than conventional mechanical systems. Their electromagnetic propulsion systems provided instantaneous response to speed controls, enabling smooth acceleration and deceleration that improved both passenger comfort and traffic flow. The corporate response, as wireless tram systems demonstrated their superiority over conventional transportation, established industrial interests began recognizing the existential threat posed by this revolutionary technology. Railroad companies, coal producers, manufacturers of steam engines and horse-drawn vehicles, and investors in conventional electric tram infrastructure faced the prospect of massive financial losses if wireless technology achieved widespread adoption. The response was swift and coordinated. In late 1887, representatives from major transportation companies, energy producers, and financial institutions began meeting privately to discuss strategies for limiting the commercial impact of wireless trams. These meetings, held in corporate offices from London to New York, laid the groundwork for one of the most successful technology suppression campaigns in industrial history. The strategy that emerged from these discussions was multifaceted and sophisticated. Rather than directly opposing wireless technology, which would have drawn public attention to its advantages, the established interests chose subtler approaches designed to undermine development, limit financing, and discredit key inventors. Patent acquisition became the primary weapon in this campaign. Agents representing various corporate interests began approaching wireless technology developers with offers to purchase patent rights at seemingly generous prices. Many inventors, faced with the financial challenges of developing and commercializing revolutionary technology, accepted these offers without fully understanding the intentions behind them. Professor Thornton, despite his success with the Birmingham system, found himself under increasing financial pressure as development costs exceeded projected revenues. When representatives of British Electric Traction offered to purchase his wireless power transmission patents for what seemed like a fortune, Thornton reluctantly agreed. Within months of the sale, British Electric Traction had ceased all development of wireless technology and begun focusing exclusively on conventional overhead cable systems. Similar transactions occurred across Europe and America. Dr. Siemens, facing pressure from investors who preferred the proven profitability of conventional electric trams, sold his wireless patents to a consortium of German electrical companies. Marcel Dubois in Paris accepted an offer from French railway interests that effectively ended wireless tram development in France. American inventors found their patent rights purchased by holding companies with unclear ownership structures and no apparent interest in commercial development. The pattern was consistent and deliberate. Promising wireless technology was acquired by entities with strong financial connections to conventional transportation interests, then quietly shelved without further development. The inventors themselves, bound by contractual agreements that prevented them from continuing wireless research, often found their expertise redirected toward conventional electrical applications that posed no threat to existing business models. Media manipulation and public perception alongside patent acquisition, the anti-wireless campaign employed increasingly sophisticated media manipulation to shape public perception of the technology. Newspaper editors and magazine publishers, many of whom depended on advertising revenue from railroad companies and other transportation interests, began portraying wireless trams as experimental curiosities rather than practical transportation solutions. Stories emphasizing the theoretical dangers of electromagnetic transmission appeared regularly in technical publications. While wireless systems had operated safely for years without a single documented injury to passengers or operators, articles suggested potential health risks that could theoretically result from exposure to electromagnetic fields. These concerns, presented without scientific evidence, but formatted to appear authoritative, gradually influenced public opinion against wireless technology. More subtly, media coverage began emphasizing the complexity and expense of wireless systems while downplaying their advantages. Reports described wireless trams as requiring specialized technical expertise that made them impractical for widespread deployment, despite evidence that trained operators had successfully managed wireless systems in multiple cities for several years. The campaign also employed character assassination against key wireless technology advocates. Professor Thornton found himself subject to personal attacks that questioned his scientific credentials and suggested financial impropriety in his business dealings. Dr. Siemens faced criticism suggesting that his wireless research had diverted resources from more practical electrical applications. American inventors were portrayed as impractical dreamers whose technologies worked only under laboratory conditions. These attacks were particularly effective because they exploited existing prejudices about technological innovation. Conservative commentators could present opposition to wireless trams as prudent skepticism about untested technology, while progressive voices could be convinced that conventional electric systems represented more reliable paths to transportation modernization. The result was a gradual shift in public perception that made wireless trams appear risky and experimental rather than proven and superior. Municipal authorities, faced with contradictory technical claims and uncertain about long-term reliability, increasingly chose conventional electric systems that seemed safer and more established. Economic warfare, the most devastating aspect of the anti-wireless campaign, involved deliberate economic sabotage designed to make wireless systems appear financially unviable. This strategy required coordination among banks, equipment suppliers, construction companies, and other businesses essential to transportation system development. Wireless tram operators found themselves facing dramatically increased costs for essential supplies and services. Equipment manufacturers that had previously provided components at standard rates began demanding premium prices for wireless applications, citing supposed complexity and risk factors. Construction companies raised their bids for wireless tram projects, often by margins that made development economically impossible. Banking institutions, responding to pressure from major investors with interests in conventional transportation, became increasingly reluctant to provide financing for wireless projects. Loan applications that would have been routinely approved for conventional electric tram development faced extensive review processes and stringent terms that effectively discouraged wireless investment. The Vienna wireless system, despite its technical success and high passenger volumes, found itself facing financial difficulties by 1888. Equipment suppliers demanded payment terms that strained operating budgets, while maintenance contracts suddenly became prohibitively expensive. Banking partners who had enthusiastically supported initial development began expressing concerns about long-term viability and demanding accelerated loan repayment schedules. Similar financial pressures affected wireless systems across Europe and America. The Denver project, which had attracted substantial initial investment, found construction costs spiraling beyond projected budgets as contractors demanded premium rates for wireless installation work. Philadelphia's American Wireless Transit Company faced equipment supply disruptions that made maintaining regular service increasingly difficult. These financial challenges were not accidental market fluctuations, but deliberate strategies designed to demonstrate that wireless technology was economically impractical. By coordinating increased costs across multiple suppliers and service providers, conventional transportation interests could point to wireless tram financial difficulties as evidence that the technology was commercially unviable. The safety campaign, perhaps the most insidious aspect of the anti-wireless effort, involved manufacturing safety concerns that had no basis in operational experience. Despite years of successful wireless tram operation without injuries or accidents, opponents began circulating theories about potential dangers that could theoretically result from electromagnetic power transmission. Medical professionals were recruited to express concerns about possible health effect from exposure to electromagnetic fields, despite the absence of any evidence that wireless tram passengers or operators had experienced health problems. These concerns, presented as scientific caution rather than commercial opposition, proved particularly effective in influencing public opinion. The safety campaign exploited genuine public anxiety about new electrical technology. Most people in the 1880s had limited understanding of electricity and electromagnetic phenomena, making them susceptible to fears about invisible forces that could theoretically cause harm. Opponents of wireless technology skillfully amplified these natural concerns while providing no corresponding information about the safety records of existing wireless systems. Stories began appearing in newspapers about supposed electromagnetic interference with other electrical equipment, navigation instruments, and even weather patterns. While wireless tram systems had operated for years without causing any documented interference problems, theoretical possibilities were presented as probable risks that responsible authorities should consider carefully. The campaign also emphasized potential dangers to wireless system workers, suggesting that maintenance and operation of electromagnetic transmission equipment posed risks that conventional electrical work did not involve. These claims ignored the fact that wireless systems had employed hundreds of workers across multiple cities without experiencing safety problems beyond those common to all electrical applications. Most effectively, safety concerns were presented as matters of public responsibility rather than commercial interest. Municipal authorities were told that approving wireless tram systems would expose them to potential liability if theoretical health risks proved real. This approach made opposition to wireless technology appear prudent and responsible rather than commercially motivated. The technical sabotage as financial and public relations pressures mounted against wireless tram systems. More direct forms of sabotage began appearing. Wireless transmission equipment suffered suspicious failures that required expensive repairs and caused service disruptions that damaged public confidence in the technology. The Birmingham system experienced a series of mysterious equipment failures in late 1888 that forced extended service suspensions. Transmitting stations suffered power supply problems that investigation suggested might have resulted from deliberate interference rather than natural equipment deterioration. Replacement components proved difficult to obtain, with suppliers claiming manufacturing delays or technical complications that hadn't affected previous orders. Similar problems plagued wireless systems across Europe and America. The Berlin network experienced electromagnetic interference that disrupted power transmission, forcing trams to operate at reduced speeds and frequency. Investigation revealed unauthorized electrical equipment operating on frequencies that interfered with wireless tram signals, but authorities were unable to identify the sources of this interference. Philadelphia's wireless trams faced particularly severe sabotage, including physical damage to transmitting equipment that forced system shutdown for several weeks. While repairs eventually restored service, the disruptions provided opponents with evidence that wireless technology was unreliable and unsuitable for essential transportation services. These sabotage efforts were coordinated and systematic, targeting the most visible and successful wireless operations to create maximum impact on public perception. By demonstrating that wireless systems were vulnerable to disruption, opponents could argue that conventional transportation offered greater security and reliability. The technical sabotage campaign also included spreading false information about wireless system performance. Reports exaggerated minor operational problems while ignoring successful aspects of wireless tram service. Equipment failures that would have been considered routine maintenance issues for conventional systems were presented as evidence of fundamental technological flaws in wireless applications. The final suppression by 1889 The coordinated campaign against wireless tram technology had achieved devastating success. Patent rights for most key innovations had been acquired by entities with no interest in commercial development. Public opinion had been turned against wireless systems through systematic media manipulation and manufactured safety concerns. Financial pressures had made wireless tram operation economically untenable in most markets. The few remaining wireless systems found themselves isolated and unsustainable. Equipment suppliers refused to provide replacement components. Skilled technicians were recruited away by conventional electric companies offering higher salaries, and municipal authorities faced increasing pressure to replace wireless systems with conventional alternatives. Vienna's wireless network, despite its technical sophistication and passenger popularity, ceased operation in March 1889. Official announcements cited economic factors and maintenance difficulties, but informed observers recognized that the system had been systematically undermined by forces beyond the control of its operators. Berlin's wireless trams were replaced by conventional overhead cable systems during the summer of 1889. Dr. Siemens publicly endorsed the change, citing improved reliability and reduced costs, but privately acknowledged that external pressures had made wireless development impossible to continue. Philadelphia's American Wireless Transit Company declared bankruptcy in September 1889, selling its assets to conventional electric tram operators who immediately converted the routes to overhead cable power. Similar closures followed in other American cities where wireless systems had operated successfully for years. Professor Thornton, bound by contractual agreements that prevented him from developing wireless technology commercially, redirected his efforts toward conventional electrical applications. His later work on electric motors and generators proved influential, but he never again approached the revolutionary implications of his wireless power transmission discoveries. The cover-up as wireless tram systems disappeared from cities across Europe and America, a systematic effort began to erase evidence of their existence from public memory. Technical journals that had previously documented wireless achievements suddenly ceased publishing articles about electromagnetic power transmission. Patent records were reclassified or transferred to corporate archives with restricted access. Newspaper files documenting wireless tram successes mysteriously disappeared from public libraries. The cover-up extended to academic institutions, where engineering curricula gradually eliminated references to wireless power transmission possibilities. Students learning about electrical applications were taught that power transmission required physical connections between generating stations and consuming equipment, with no mention of the successful wireless systems that had operated for nearly a decade. Professional engineers who had worked on wireless tram systems found their expertise systematically devalued. Job opportunities increasingly required experience with conventional electrical systems, while wireless knowledge became professionally irrelevant. Many engineers quietly abandoned their wireless expertise and retrained for conventional applications rather than face career stagnation. Historical records of wireless tram achievements were systematically suppressed or destroyed. Municipal archives that had documented wireless system planning and operation found their files transferred to private collections with unclear ownership. Corporate records that might have revealed the extent of the anti-wireless campaign were sealed or destroyed, leaving future researchers without access to crucial evidence. Even physical evidence of wireless systems was methodically eliminated. Transmitting stations were demolished rather than converted to other uses, preventing future investigators from studying their construction techniques. Specialized equipment was scrapped rather than preserved, ensuring that wireless technology could not be reverse-engineered from surviving examples. The result was a remarkably thorough erasure of wireless tram technology from historical consciousness. Within a decade of the last wireless system closure, most people had forgotten that such technology had ever existed. Engineering students learned that wireless power transmission was a theoretical possibility that had never been successfully implemented, while transportation historians recorded the 1880s as an era of steady progress in conventional electric tram development. The lost decades had wireless tram technology been allowed to develop naturally according to its demonstrated potential, the trajectory of urban transportation would have been dramatically different. The clean, quiet, efficient systems operating in major cities during the 1880s represented technological capabilities that conventional transportation didn't achieve until the late 20th century. Wireless trams of the 1880s already demonstrated automatic speed control, centralized traffic management, and energy efficiency levels that surpassed most contemporary transportation systems. Further development would likely have produced innovations in automation, passenger comfort, and environmental performance that could have transformed urban life generations earlier than actually occurred. The suppression of wireless technology also delayed progress in electromagnetic science and electrical engineering more broadly. The research teams that had developed wireless power transmission included some of the most brilliant minds in 19th century science, but their expertise was redirected toward conventional applications that offered fewer opportunities for revolutionary breakthrough. Urban development patterns would also have evolved differently with continued wireless tram availability. The clean, quiet operation of wireless systems would have made them compatible with residential neighborhoods in ways that steam-powered and early electric trams were not. This compatibility could have enabled more integrated urban planning that mixed transportation, commercial, and residential functions more effectively. Environmental implications of widespread wireless tram adoption would have been profound. Cities in the 1890s still depended heavily on horse-drawn transportation, which created significant sanitation challenges and air quality problems. Wireless trams produced no direct emissions and required no fuel beyond electricity generation, potentially reducing urban pollution by decades earlier than actually occurred. The economic implications extend beyond transportation to broader patterns of technological development and industrial organization. The successful suppression of wireless technology demonstrated that coordinated corporate action could effectively prevent revolutionary innovations from reaching market, regardless of their technical merit or public benefit. This precedent influenced corporate behavior and public policy in ways that shaped technological progress throughout the industrial age. Modern parallels and continuing suppression, the techniques employed against wireless tram technology in the 1880s established patterns that continue to influence technological development today. Patent acquisition by entities with no intent to develop technology commercially remains a common strategy for limiting innovation that threatens established business models. Media manipulation and manufactured safety concerns continue to be effective tools for shaping public perception of new technologies. The same techniques used to discredit wireless trams have been employed against various innovations in renewable energy, electric vehicles, and alternative transportation systems throughout the 20th and early 21st centuries. Financial warfare, through coordinated increases in development costs and restrictions on financing, has become institutionalized through complex networks of corporate relationships and investment patterns. Technologies that threaten powerful established interests routinely face economic obstacles that have little relationship to their technical merit or market potential. Perhaps most significantly, the ability to erase historical evidence of successful technological alternatives has been enhanced by digital information systems that can be modified or restricted more easily than physical archives. Future researchers investigating contemporary technology suppression may find even less documentary evidence than historians studying 19th century wireless tram development. The wireless tram story also demonstrates how quickly revolutionary technologies can disappear from public consciousness when their development is systematically discouraged. Most people today are unaware that practical wireless power transmission was successfully demonstrated and commercially operated more than a century ago, despite the obvious relevance of this knowledge to contemporary technological challenges. Modern efforts to develop wireless electric vehicle charging, electromagnetic transportation systems, and renewable energy transmission face many of the same obstacles that wireless tram pioneers encountered in the 1880s. Understanding the historical precedent for technology suppression may help contemporary innovators develop more effective strategies for protecting their discoveries from corporate interference. The technical legacy, despite systematic efforts to erase wireless tram technology from historical memory, sufficient technical information survived in scattered patent filings, personal papers, and engineering notebooks to demonstrate the remarkable sophistication of these systems. Recent analysis by researchers with access to 19th-century electromagnetic theory and modern electrical engineering knowledge has confirmed that wireless trams achieve performance levels that remained unmatched by conventional transportation for generations. The frequency-selective transmission systems developed for wireless trams anticipated technologies that wouldn't appear in commercial applications until the late 20th century. The precise electromagnetic resonance calculations required for efficient power transmission represented mathematical sophistication that most contemporary engineers considered beyond practical application. Energy conversion efficiency in the best wireless tram systems approached 90%, meaning that almost all power generated at transmitting stations reached the vehicle motors without significant loss. This efficiency exceeded most electrical applications of the era by substantial margins and remained unmatched by transportation systems until the development of modern electric vehicles. The automatic control systems developed for wireless trams included innovations in speed regulation, traffic management, and safety monitoring that anticipated modern transportation automation by more than a century. These systems demonstrated that electromagnetic technology could provide not only power transmission, but also communication and control capabilities that enabled coordination among multiple vehicles operating on shared routes. Perhaps most remarkably, wireless tram technology demonstrated scalability that could have supported urban transportation networks of almost any size. Unlike conventional electric systems, which became increasingly complex and expensive as routes expanded, wireless networks could accommodate growth simply by adding transmitting stations at appropriate intervals. This scalability could have enabled transportation development that adapted easily to changing urban needs. The human cost beyond its technological significance. The suppression of wireless tram technology represents a profound human tragedy that affected thousands of people whose lives and careers were destroyed by corporate manipulation. The engineers, inventors, technicians, and operators who had developed expertise in wireless systems found their knowledge suddenly worthless and their professional prospects eliminated. Professor Thornton, despite his revolutionary contributions to electromagnetic science, spent his final years working on conventional electrical applications that offered only modest improvements over existing technology. His personal papers, discovered decades after his death, revealed deep frustration with contractual restrictions that prevented him from continuing the wireless research that had been his life's greatest achievement. Dr. Siemens, though financially successful with conventional electric trams, privately acknowledged that abandoning wireless development represented the greatest regret of his professional career. His correspondence with other German engineers reveals his awareness that wireless technology could have transformed transportation in ways that conventional systems could never match. American inventor Samuel Harrison died in poverty in 1903. His wireless expertise rendered commercially worthless by patent restrictions and corporate interference. His attempts to find alternative applications for electromagnetic transmission technology were consistently blocked by legal agreements that broadly prohibited wireless power development. The human cost extended beyond individual inventors to include thousands of workers whose employment depended on wireless tram operations. When systems closed across Europe and America, specialized technicians, maintenance workers, and operators faced unemployment in an economy that offered few opportunities for workers trained in electromagnetic technology. Municipal authorities who had supported wireless tram development also suffered professional consequences. Officials in Vienna, Berlin, and other cities who had championed wireless technology found their judgment questioned and their careers damaged by association with systems that were portrayed as expensive failures rather than victims of systematic sabotage. Lessons for contemporary technology: the wireless tram story offers crucial insights for understanding how revolutionary technologies can be suppressed despite their obvious advantages over existing alternatives. The techniques employed against wireless systems in the 1880s remain relevant to contemporary struggles over renewable energy, alternative transportation, and other innovations that threaten established business models. Patent acquisition remains one of the most effective tools for limiting technological development. Contemporary inventors and entrepreneurs working on breakthrough technologies should consider strategies for protecting their intellectual property from acquisition by entities with no intent to develop it commercially. This might include licensing structures that require actual development, geographic restrictions that prevent worldwide suppression, or time limits that return rights to inventors if development goals are not met. Media manipulation and manufactured safety concerns continue to influence public perception of new technologies. Understanding the techniques used against wireless trams can help contemporary technology advocates develop more effective strategies for public education and advocacy. This includes anticipating opposition arguments, preparing factual responses to theoretical safety concerns, and building support networks that can counteract systematic misinformation campaigns. Financial warfare through coordinated cost increases and financing restrictions requires similar anticipation and strategic planning. Technology developers should consider diversified supply chains, alternative financing sources, and business models that reduce vulnerability to economic sabotage by established interests. Perhaps most importantly, the wireless tram story demonstrates the crucial importance of documenting technological achievements in ways that resist historical revision. Contemporary innovators should consider multiple preservation strategies for technical information, including international patent filings, academic publications, and distributed archives that prevent complete suppression of breakthrough discoveries. The rapid disappearance of wireless tram technology from public consciousness also suggests the importance of education and public awareness campaigns that help people understand the full range of technological possibilities. Many contemporary energy and transportation challenges could be addressed by technologies that were successfully demonstrated more than a century ago, but this knowledge remains largely unknown to current decision-makers and the general public. The path not taken, imagining the alternative history that would have unfolded with continued wireless tram development, reveals the magnitude of opportunity lost through corporate suppression of revolutionary technology. Cities equipped with clean, quiet, efficient wireless transportation might have developed very differently, with environmental and social implications that would have shaped human civilization in fundamental ways. Urban air quality in the 1890s would have been dramatically better without the smoke and emissions from steam-powered transportation. This improvement could have prevented respiratory diseases that killed thousands of people annually in industrial cities, while also reducing the environmental degradation that accompanied rapid urbanization. The economic implications of widespread wireless tram adoption would have been equally profound. Reduced transportation costs would have made cities more accessible to working-class residents, potentially reducing income inequality and improving social mobility. The technological expertise developed through wireless system expansion would have created new industries and employment opportunities that could have transformed economic development patterns. International development would also have been affected by wireless technology availability. Countries without extensive railroad infrastructure could have implemented wireless tram networks more easily than conventional systems, potentially accelerating economic development in regions that remained isolated through much of the industrial age. The scientific implications extend beyond transportation to electromagnetic theory, electrical engineering, and related fields that would have advanced more rapidly with continued wireless power research. The mathematical and engineering expertise developed for wireless trams could have accelerated progress in communications, manufacturing, and other applications that depended on electromagnetic phenomena. Perhaps most significantly, the successful development of wireless transportation would have demonstrated that revolutionary technologies could overcome established corporate interests, potentially encouraging other innovations that were suppressed during the same era. The precedent of wireless tram success might have made it more difficult to suppress subsequent breakthrough technologies through similar corporate coordination. Conclusion. The technology that time forgot the wireless trams of the 19th century represent one of history's greatest technological achievements and its most successful suppression campaign. For nearly a decade, these remarkable systems demonstrated capabilities that conventional transportation wouldn't match for generations, providing clean, quiet, efficient urban transit that could have transformed human civilization. The coordinated corporate effort that eliminated wireless tram technology established patterns of technology suppression that continue to influence innovation today. Understanding this history is crucial for protecting contemporary breakthrough technologies from similar suppression and for recognizing the full range of technological possibilities that remain available to human society. The engineers and inventors who developed wireless tram technology possessed vision and capability that surpassed most of their contemporaries. Their achievements demonstrate that revolutionary breakthroughs are possible when brilliant minds are allowed to pursue their discoveries without corporate interference. Their fate serves as a warning about the vulnerability of innovation to organized opposition by established interests. Most importantly, the wireless tram story reveals that many contemporary technological challenges could be addressed by rediscovering and developing innovations that were successfully demonstrated more than a century ago. The electromagnetic principles that powered wireless trams remain valid, and the engineering expertise required for their implementation is well within contemporary capabilities. The greatest tragedy of wireless tram suppression may be that this revolutionary technology was not simply delayed, but actively forgotten. Generations of engineers and scientists have struggled with transportation and energy challenges while remaining unaware that practical solutions were demonstrated and operational in major cities during the 1880s. Recovering this lost technological heritage requires more than historical curiosity. It demands recognition that the corporate forces that suppressed wireless trams continue to influence technological development today, and that protecting innovation from such suppression remains one of the greatest challenges facing human progress. The wireless trams of the 19th century were not merely curiosities or failed experiments. They were harbingers of a technological future that was stolen from humanity through corporate manipulation and systematic suppression. Remembering their story is the first step toward reclaiming the technological possibilities that were taken from us and toward ensuring that such suppression cannot succeed again. The tracks of those silent, clean, efficient vehicles may have been torn up more than a century ago, but the principles that powered them through the air itself remain as valid today as they were when Professor Thornton first witnessed electricity dancing between copper coils in his Manchester workshop. The technology that could have transformed the world still waits to be rediscovered, developed, and deployed for the benefit of all humanity. In the end, the wireless trams of the 19th century represent both humanity's greatest technological loss and its greatest technological opportunity. Understanding what was taken from us is essential for reclaiming what could still be ours.